Hi, everyone. We'll be trying to demystify machine learning today, and if you don't hear my mic, just kind of raise your hand and I'll start talking louder or whatever, readjust it. But let's start. So machine learning is one of those words, I'll just keep it here. Machine learning is one of those words that's been really hyped up recently, and when something is so hyped up, it's really hard to distinguish signal from noise. And my hope today is that we'll be able to demystify machine learning. So in order to do that, we need to answer a fundamental question of what it is. So what is machine learning? Machine learning is a branch of artificial intelligence, and plainly put, it uses math and statistics to learn about data and predict things based on that data. So now that we know what it is, usually I like to figure out where can I use it in production before I dive deep into the technology. So we're going to look into that. Let's look at the first use case, which is widely popular on the internet, and it's recommendation engines. So if you ever bought a book off Amazon, at the end, that's a good point.
Clip it on your shirt, or you can.
If I do, I have to, but it's okay. All right then. Okay, so recommendation engines. If you ever bought a book off Amazon and you kind of go through the process, and at the end you'll see a paragraph that says you might also like these items, and then there's going to be a list of items that are similar to the items that you just bought. The way that Amazon compiles that list is through machine learning. They look at your search history, they look at your purchasing history, a whole bunch of stuff, and they compile a list, and turns out the list is pretty good. When I bought a book off Amazon, I think it was just a general programming book. This is what it came out at the end. If you watch Netflix or YouTube or Hulu, at the end you'll get recommendations about your next movie or your next show. Kind of works with the same principle. The next really cool one is OCR, or optical character recognition. So if you ever took a picture of your check with your banking app, there's a really high chance that there was a machine learning algorithm behind the scenes that read the text off the image and deposited that to your bank account. Next one that I'm really passionate about is cancer prevention. So doctors around the world are using machine learning to prevent cancer. So it could be radiologists that look at scan images of your bones or your cells, and they have algorithms that detect anomalies in those images. They can also look at DNA samples and kind of see how well is your DNA structured and predict how likely are you going to have a certain type of cancer, which if you just think about it for a second, that's pretty amazing. Another cool one that's going around, especially San Francisco, are self-driving cars. In the heart of a self-driving car is a machine learning algorithm. It helps the car learn how to drive, when to turn, how to park, pretty much everything about the world around it. It's a pretty sophisticated algorithm, but it's still a machine learning algorithm with a bunch of sensors attached to it. So now we know a few use cases. Of course, there's more, but I'm not gonna spend a lot of time on them. We have to figure out when can we use it and when should we use it. We all heard about SQL probably. So anytime you have to analyze historical data and answer questions like, hey, how many customers do we have next month? Or what's our average revenue in the past year? Or what was our churn rate? Anything like that can be answered with SQL, and you should use SQL. It's great. It's pretty amazing. It's proven over the years to be pretty scalable. However, if we have to predict the future, that's when machine learning comes in. So if you have to answer questions like, what's our revenue going to be in 5 years? Or what's the price of a product in 3 weeks? Or is this a picture of a cat or a dog? That's when machine learning comes in and helps you out in answering those questions. So this part specifically is pretty near and dear to my heart, because when I started doing machine learning, I had a huge problem of figuring out how the heck does math work with machine learning. And I heard all these talks and people have PhDs, and it's a whole shazam. But my hope with this section is to give you at least a little bit of intuition of how this things work on a very simple example, and then you can build on top of that after this. So this is a very simple high school equation that we probably all did at some point. And we have, there's, thetas are Greek letters, but you can think of any letter that you like. And me, doing a bunch of Stanford courses, people like to use Greek letters. But on the left, you have h of theta. On the right, we have theta 0 plus theta 1 times x1. So if you calculate the things on the right, you're going to get a result on the left. Next equation is a little bit simpler than the previous one because we only have to figure out x1. Everything else is kind of filled out for us. Thetas are replaced. And if we have x1, we're gonna have answer to h of theta. What's cool about this equation is that it's a backbone of an algorithm called linear regression. If you did statistics, you did regression. And in order to kind of understand how it works, let's pretend we're trying to predict someone's salary based on their years of experience. Of course, in real life, predicting someone's salary, there's many factors, but for our use case, it's just years of experience. So what a linear regression algorithm would do is it would go through a certain process that we'll talk about later. It would figure out these thetas, and then then it would plug in years of experience instead of x1. So if you have 5 years of experience, the equation goes something like this: 3 plus 0.2 times 5, and whatever the result of that is would be your salary in thousands, for example. And that's about it. That's all that linear regression is. Of course, when as models grow more complicated, the math gets more complicated. But all that a model is an equation behind the scenes that spits out numbers. Yeah, that's all there is to it. I found that a lot of people get turned off by machine learning because they see math and numbers. And while I would lie if I say that it's not hard as things get more complicated, if you stick with it, I think it will click at some point. We'll come back to this a little bit later, but now let's talk about types of machine learning algorithms. There's 2 types. The first type is supervised machine learning algorithms, and those are the algorithms that work with labeled data. What is labeled data? So imagine you have a picture of a cat and a picture of a dog. And with a picture of a cat, you put a labeled cat, and for a picture of a dog, you put a labeled dog. You feed those 2 pictures in an algorithm goes, okay, this is the picture, this is its label, and that's how it learns what is what. On the other hand, you have unsupervised machine learning algorithms where there's no labeling, and an algorithm has to figure out all that on its own. So today we'll be talking about regression. And regression is used to predict continuous values. All continuous values mean are numbers. So if you ever need an answer to the question of, for example, I'll come back to this, but what is the salary of my next employee? Or what is the mortality rate in a country X? Or what's the weather going to be like in 5 days? Or I just did a time series example where we had to predict a price of a certain product based on a bunch of stuff. So the output is a single number in all those cases. That's where regression comes in. Linear regression is called linear because the kind of the relationship between 2 variables grows linearly. Linearly, that's not a word. But it'll be a little bit clearer in a second when I show you a graph of why is it called linear. So we go back to this equation again, and there's this thing called dependent variable. So what dependent variable is, that's h of theta. I don't know if you can see or you can't see, but h of theta is called a dependent variable. What that means is it's the thing we're trying to predict. So if we go back to our salary example, that will be the salary. Theta 0 is a constant, theta 1 is a coefficient, and x1 is called an independent variable. In our salary example, that will be years of experience. So theta 1 is kind of interesting. The coefficient is really interesting because it describes the relationship between independent variable, also called a feature, and a dependent variable. So if you drive a red car, and we're trying to predict your salary, a coefficient will be pretty low because the color of your car doesn't matter. However, years of experience do matter, so a coefficient will go up. These are also called weight sometimes, but people use different words for the same thing. We also mentioned this equation, which is the same version of the previous one, and I told you that regression goes through a certain process of figuring those out. And we're going to talk about that process right now. The algorithm is called gradient descent. It's a pretty famous machine learning algorithm. And in order to kind of get it, I'm going to show you a plot, and then I'm going to walk you through it of how it works. All this is trying to solve the problem of salary and predicting salary based on years of experience. So this is a graph I'm pretty proud of. I made it myself. And x of 1 is on the x-axis, and it represents years of experience. H of theta is salary, and it's in the y-axis. We have a bunch of red dots. Those red dots are real data points. So you ran a SQL query, and you pulled out 50 employees and their years of experience and salary. And then you have that straight line. That's why this algorithm is called linear regression, because values grow linearly. Linearly, sorry. And basically that line is drawn with those data. So if I go back, 3 here is y-intercept on the y-axis, and 0.2, and 0.2 is the slope of the line. So if you look at this picture for a second, it makes sense. It's pretty easy to predict someone's salary if we have that line. So I'm going to walk over here. So I'm going to draw, because I don't have a laser. If somebody has 5 years of experience, right? You would find 5 on the x-axis. You would draw a line up, and you would read off of y-axis. So the question really becomes, how do we find this line? And that's where kind of all the fun stuff comes in. That's when the algorithm gradient descent comes in. So what happens is, when a machine learning algorithm starts learning, they don't know anything, right? So they just guess. So an algorithm is going to guess status, or it's going to guess this line. And for example, it's going to draw a line right here. And then it's going to try to predict these red dots. Basically, it's going to try to predict salaries based on the given years of experience. It's going to predict those, and then it's going to ask itself, okay, how much am I wrong? And the answer to that is something called a cost function. It's going to calculate a cost function. And what that number means is basically you're wrong this much. It's just a single number that represents how wrong are your predictions, right? So then what it's going to do is it's going to draw another line. It's going to do this. And then it's going to ask itself again, the whole process. It's going to calculate the cost function. It's going to keep doing that a few times. And after a few times, it's going to pick a line that has the lowest cost. Why the line with the lowest cost? Well, if you think about it, when you draw a line here, the straight line over here, the cost is going to be pretty high. Why? Because the difference between the predicted values and the actual values is pretty big. However, if you have this line, the difference between predicted values and the actual values is pretty small. So you want the line that has the lowest cost, because that means that your predictions are very accurate. They will never be 100% accurate. If they are, you're doing something wrong. So given, of course, that data has a linear trend. If your data is going wavy, or has a curve or whatever, then you can't use linear regression, because the data doesn't grow linearly. Man, I'm having trouble with that linearly word. Cool. All right, so that's about it. It's all about, even neural networks work like this. So it's all gradient descent. Of course, there's a bunch of optimizations on top of this that can make it go faster, but it's all about, hey, I'm going to guess randomly what these thetas are, and then I'm going to do it a bunch of times until I get it right. That's really all that it is. It's a simple example, and it's the best one to learn on. And if it didn't click immediately, that's completely okay. It took me a few times to kind of wrap my head around it. But once you do, you know 80% of machine learning. I mean, maybe 75. But that's really, gradient descent is kind of the staple, and that's how all algorithms nowadays work. All right, so now we kind of know how to figure out those thetas, and we have our algorithm, and it can predict salaries, but how do we put this thing in production? So I'm going to talk about that a little bit. That's a talk on its own, but I had a really good feedback a few times ago when I gave this talk about that I didn't have this slide, so I'm going to talk about it really quickly. So there's 4 steps. I know I have only 3 steps there, but the first step is defining a problem. So whenever you're trying to solve anything, you need to make sure that everybody's on the same page of what it is that you're trying to solve. Once you are all on the same page, you have to get the data. Now, getting the data can be done in multiple ways. Database, CSVs, Excel files, Kafka streams, whatever works, for you. Once you get the data, this is kind of the same step, but once you get the data, you have to examine the data and clean it up and make sure it's ready for the algorithm and kind of make sure that it's ready for the next step, which is basically picking the algorithm. Now, a lot of machine learning is going to neural networks, which we can talk about later. Why is that? But you have to pick the algorithm. If you're doing classical machine learning, there's a bunch of them. You have to know which one is good for which problem. Sometimes you don't, and you try a few of them, see which one works best. Once you pick the right algorithm, with experimentation, you have to implement it. The demo that I'm about to do is I already did all the steps except the last one. So, when you go home or when you go to your work and want to do these things, you should kind of be aware of the whole pipeline. Sometimes these things are, in bigger companies, they have data engineering teams, they have machine learning teams, they have data science teams, and each owns a different box. Sometimes in smaller companies, one person does all of it. It just kind of depends. And yeah, let's get to coding. Hopefully this goes well. The questions are at the end, if you don't mind. All right. Yeah, sorry. Questions are at the end. I forgot to say that. All right. So I'm using something called a Jupyter Notebook. If you've never heard about it, it's just an IDE in a browser. It lets you run Python. If you've never seen Python, it's the same as Ruby. If you've never seen Ruby, it's the same as Smalltalk. So it's kind of, all the same. All right. So can you see this? How about now? Nice. Okay, so I didn't want to remember a bunch of imports and pretend to know a bunch of imports, so I just imported them in advance and I cheated. And this last part is for plotting. So I'm going to explain what these libraries do. So there's NumPy, which is used for manipulation of arrays. By the way, this is going to be all on GitHub, so you can take a look at it. Matplotlib is for plotting graphs. Pandas is actually one of my favorite libraries, and what it does is it takes a CSV or an Excel and it makes it into something called a data frame, which is essentially Excel in code. So you can do pivot tables, you can do different things in code, just as you would with Excel, and that turns out to be really useful when you're doing machine learning. There's this famous library called scikit-learn. In this specific line, we're importing train test split, which we're going to need to split test data and train data, and I'll explain why that's important in a second. And then there's a linear model and importing linear regression, which is, instead of me doing this from scratch, there's already somebody that did it for me, and it basically does that thing that I just explained with the graph and finding the the weights and stuff. Although, however, I would highly recommend building one from scratch, because that's when you kind of figure out how it really works. Cool, so the first thing we need to do is import a data set. We'll be using a data set called salary data, which it has, I just found it online, it's a random data set. So we have to do this. All right, so that's because I didn't import my library. So it's like a cell by cell, so we have to run each cell separately. So now I have it, and if I do dataset.head, it basically spits out a part of that CSV because it's the same thing, just larger. This is just a sample of that CSV. As you can see, we have years of experience, which is what our X1, and then we have salary, which is our H of theta or Y. So what we need to do first is we need to split out dependent and independent variables. Why? Because if you remember the equation, you have two parts. You have a part that you're trying to predict, and you have a part that you're calculating the prediction with. So when you're using this linear regression algorithm, you have to pass it, two things because it expects x's and y's. So the way to do that is there's multiple ways, but we're going to do it manually. So X is basically data set. I'll explain what these do in just a second. So all the rows, this, and instead of you can call this H, right? But it's the same thing. All right. So what is X? So in pandas, you can do this thing called iloc, which selects certain rows and columns. So the first item is rows. So we want all the rows, and the second item is columns. We want all the columns except the last one, which in this case is just years of experience. For Y, we say we want all the rows and the last column. The last column is salary, which is the thing we're trying to predict, right? Remember, this is Y is the thing we're trying to predict. That's the H of theta from the slides. Okay, so now that we have this, we have to do something called splitting the data into testing and training. So the reason why we do this, if you think about classic software development, you write tests to back your program. So TDD or BDD or whatever your flavor of testing is, but you end up with some sort of an automated test to prove that your code is working. So there'll be questions at the end. And so to prove that your code is working, and basically what we do in machine learning instead is we have the whole data. Let's say it has 100 data points, 100 rows, and we take the last 20 rows and we hide it from the model. And we train the model with the first 80, and then we test the model with the last 20 to see how it does. It's very common. The percentage of testing data differs based on a person or company. I like to use 20% because people that did this for many years than me told me to use 20%, but you can kind of play around with that and see if you need more data. Then if you need I think I need more data to train my model, then you maybe test only on 5%, but then you run into different problems. But in general, a good rule of thumb, 20% of your data can go into the test data. Okay, so now we have to do that, and there's one handy function called train test split in scikit-learn, and we're going to use that. By the way, how am I doing on time?
You had 24 minutes.
Nice. Okay, good. We're finished on time. Okay, so X train, X test. I'll explain what this is in a second. Y train, Y test. And then you pass it this, and then I'm going to do this trick. Okay, so let's talk about this. Python has this thing called decomposition, which basically you can return multiple values out of, I actually don't know if it's called decomposition. I forgot the official name, but I call it decomposition. And what happens is when you return a value, you can return multiple values, and then you can kind of accept them in that way when you call the function. So here, this function is returning 4 values in this order, and we're accepting them in this way. Okay, so you pass, your x and y's, and I call this thing random state 0. The reason why I call this is in linear regression, there's some randomness, and the results always come off a little bit different. There's a few reasons for that. But in order to get the same result every time, for demo purposes, I put this random state 0, which basically means don't add the random bias to the thing. Okay, so we got that. We're going pretty strong. We have everything set up to train the model. Now, we're going to train the model. It's kind of amazing how simple it is to do that. So what we're doing here is we're instantiating a class called linear regression, which is the linear regression model that we just talked about. And basically, we have X train and Y train. We're training the model with X train and Y train. And this is basically the fit method. What that does is it finds that line. If you go back to that line, it finds it. Or the other way to think about it is it finds those weights, or it finds those coefficients and thetas, and it finds the parameters. Okay, let's run this and see what happens. All right, that was pretty fast, given that this data set is pretty small. But it's pretty fast. So now what we can do is we can predict things. And if you remember, I kind of separate the data set into training and testing, and training and testing. So this is not 4 data sets, it's the same data set, except it goes in train pairs and test pairs. So what I can do now is I can give my model the data that it hasn't seen before, that hides an X test, and then I can tell my model, hey, predict h of theta or predict y, and then we can compare it to y test, because those are the real values, right? So we're going to do that really quickly. Let's see how this works. Okay, so let's see what ypred is. So ypred is an array. It basically says these are all the predicted values based on these x's. And we can see what real y test values are. So let's kind of manually compare them. So the real one is 37. We predicted 41,000. Not that great, but not super bad. The real one is 122, 391, 123, 597. Better. 57, 65. 63, 63. So you can go manually and kind of inspect them, but one of my favorite ways to do these things is to visualize if I can. Sometimes the data is in 3, 4, 5, 6, 7D space, so you can't really visualize it that easily. But when it's in 2D space, it's pretty to visualize it, and you can easily see what's going on. Okay, so let's do that. All right, so there's a few things going on. So the red colors are our training data set, right? So it's just the data that we use to train the model. On y-axis, we have a salary. On x-axis, we have years of experience, right? So the blue ones are the data set that's in our testing data set. So the data set that we hid from our model, and we said, hey, we're going to test our model based on this. So these are the actual values of that thing. The orange ones are the ones that we predicted for that testing data set. So if you look closely, I don't know if you can see, I think I have to zoom in a little bit more for you to see that. Yeah, I think that's better. You see orange dots, right? Can you see orange dots? All right, nice.
4.
I can kind of like circle around. So here you have an orange dot and a blue dot. So we were pretty good with predicting it. Here we have an orange dot and a blue dot. Again, pretty good at predicting it. Orange dot and a blue dot, pretty good. There's 2 orange dots here. One is for this one is for this one, so we were pretty off. Here we have an orange dot and a blue dot, that's pretty close. Here we have an orange dot and a blue dot, and then we also have 2 orange dots that are correlating to these 2, so we were pretty off on these 2. But overall, our model is doing pretty fine, I'd say. So That's about it for the demo. There's this exact code lives in GitHub. I'll share my GitHub repo in a minute here. As all presenters, there's always fun stuff about me. So here it comes. I spared it for the last because that's the least important thing in this talk. But I like to train dogs, specifically working dogs. It's kind of thing I do on the side. This is me being a helper. I can talk about it later, but basically, in essence, it's a sport, and I train working dogs. This is me. This is my so my GitHub is this. This is my Twitter. This is my website, and this is the company I work for. It's called ScriptDrop. We're hiring a bunch of people. So if you want to join us, go on this link, and we basically do prescription delivery, and we help our patients get their medication safely and Q&A. Yes, sir.
When you're judging the quality of your model, why are we not looking at something like R-squared, which is a standard method of evaluating linear regression models?
Yeah, so that's a good question. So our mean square error is a way to evaluate. It's a cost function, and I didn't really want to burden people with a cost function. I just kind of wanted to mention it, what it is. But mean squared error is a way to evaluate a model. I like to see things visually and show things visually, but linear regression does use mean squared error by default. Hopefully that answers the question. Yes, sir.
I was going to ask you about if you would use the psychic metrics on there, or precision in
Yeah, I did. I did, yeah. I just didn't want to. That's a good idea. I did use that, but not here, just because I didn't want to burden people with information. Which one is it?
This one for model selection, so you can do a validation set.
Yeah, I did use that. That's a pretty good one too.
All right.
Yeah, I just didn't want to burden people with. My whole point was this is the kind of at least how it works a little bit, but I didn't want to burden. That's a good idea. Thank you. I appreciate it. Yes, sir.
Are there libraries available for more complex things like multivariate, nonlinear?
Yes. Yeah, scikit-learn does all that. Yeah, scikit-learn will help with that for sure. Yes, sir.
So I think thank you for the demystifying. Basically, it's simple mathematics.
Correct. That was the whole point.
The real question is, how do I get the idea which function I should use? You did a linear regression, but I might have another
Problem.
connection between my input data.
Yeah.
So I think this is the most difficult part to get the idea, how might the data be connected?
Yeah, so that's a good question. Go on.
What mechanisms do exist to get an idea?
That's a good question. Yeah, so the first thing that I personally do is I look at my data set and see what it is and what am I doing, and then I basically visualize a bunch of things if I can. I look at a graph and I see, what are the curves, what am I trying to predict, how can I do this, right? And then really that's when kind of the answer sucks. It's more of an art than a science in picking the right algorithm. It's kind of like people have these discussions about neural network architectures and all of the answers are right at the time. Of course, if your problem is multivariate and you have a linear regression, you shouldn't use linear regression. But what I do is I visualize the data, I try to guess, do my best estimate, and I try it. There's also algorithms that will help you determine which algorithm you should use, like grid search and different things, a little bit more advanced of a technique. So you can look into those. But I think at the end it comes down to visualizing and making your best estimate with the information that you know. One thing that I would, if you're not doing neural networks, even if you do neural networks, there's this thing called PCA, which basically, principal component analysis, which basically reduces the amount of features that you have, the amount of x's, and the less x's you have, the easier it will be to visualize things and decide. But there's also a trade-off where a lot of people that are really good at machine learning argue that you don't want to remove variables, like in classical statistics. You want to keep the non-linearities. That's kind of like a long answer to your question, but try visualizing it, make it a best guess, or try using an automated solution, see how it works. There's not really like, oh yeah, do this. Yes?
You mentioned something earlier about how more and more stuff is going towards the neural network-based stuff. I've heard that's because it requires less feature engineering. Is
Correct.
that the main reason? Is there other reasons why the industry is going that way?
Yes. So when you're doing these things, like for example in regression, you have to, even though you have a data set and you think you know the features, you're not always right. And sometimes you have to design the features. And there's this whole section of machine learning called feature engineering, which basically says, let's come up with the best features for this model. Sometimes that's really hard. And especially in complex problems, and people are just bad at that, like as humans. So what the main advantage of neural networks is they come up with all the features. So it doesn't really, the feature engineering piece almost goes away. Not entirely. You still have to do a little bit of it in some instances, but a lot of it just goes away. And that's one of the main advantages to neural networks. Yes, sir.
I was taking a course on data science a couple months ago, but I got kind of lost in some of those later dash stuff with like matrix multiplication and stuff like that.
Yeah.
Do you have any good resources to look at?
I do. I do. So there's this elementary school website called Math is Fun. It's one of the. It sounds ridiculous, but let me. Well, this is not the main resource, but I don't know how their search works. Let's see. I didn't spell that right, but how to multiply matrices. All right. So this is one. I use, without any shame, I have this screenshotted, and when I forget which one goes when, I just look at this. Andrew Ng does the same thing, so if he can do this, I can do this. If you don't know who Andrew Ng is, he's considered one of the fathers of machine learning, modern machine learning, amazing guy, look him up. So this is one. There's a course called, where is it? EDX. An EDX. There's a course called Math for Machine Learning. Essential math for, not the R edition. Well, you can do the R, but I did the Python. It essentially goes over, hey, linear algebra, vectors and matrices, statistics probability, calculus, differentiation, optimization, equations, function graphs. So this gives you a really good, like if you can do these things, you will know enough to at least skim through a paper, which is insanely valuable. And once I think a good goal to have is I want to be able to read a paper through and through, like an academic paper. Once you can do that, you're well on your way of doing that. Yes, sir.
Are you able to talk a little bit about like maybe what implementation would look like on computing instances for quality refinement?
I didn't hear half of that. I just heard computing instances.
Are you able to talk a little bit about what implementation would look like for computing instances for quality refinement?
We can talk about it later. I think it's a different crowd, so we can just offline if you want to, for sure. Yes, sir. Lady, sorry.
I was just gonna say, whoever asked for like one of the resources, you don't want to stare at a screen and you like comic books. There's the manga guide to linear regression. It's really awesome.
Okay, yeah.
There you go. What else? Last call, questions. Yes, sir.
What about grooming the data, getting rid of data points that might be bad?
Yeah. So that depends on the problem. What are you trying to solve? But one of the first things is, okay, let me look if I have, if I'm predicting the prices of a house, and one of the key things is square feet. Let's look at the rows and let's look at all the data and see if I have any missing values. So if you have missing values, you would want, get rid of those. Then you want to see if you have, you have to make sure the data is normalized, standard deviation, all that stuff. Then you can do sort of PCA style, principal component analysis thing, where you can reduce the amount of features. That works sometimes. So those are usually the things I try to do with the data set. Yes, sir.
One more. What about continuous input? Data?
I like your questions. We can do them later. I just don't want to go off the. Yep.
How do you do a model that has online learning where it takes in streams of data like that?
That's a good question. So the way I usually, all the problems that I'm solving, none of them require, we have to learn real time. Like, if you think about it, really, a lot of, unless you're Netflix or Facebook scale, you'll be fine if you learn, like, for example, our models learn every 5 days, right? So after 5 days, you run the model, you evaluate and see, hey, my model is better than the previous time, and I use it. You can use. I haven't implemented anything real time recently, but I heard people use Kafka a lot and listen for event streams and then train models like that.
So are you saying that we take the whole batch in, have it spit in a queue, and then when the batch fills up, we
Correct.
train the model?
Yeah, and it works perfectly fine.
Doesn't Keras have a way to set a model as an online thing and typically want to generate their class?
I think so. I actually haven't. Keras, yes, it does. Yes, but I didn't have a need for that. It's just like none of my models have to be real time.
Is there any easy way to know you're not overfitting something?
Okay, so
Maybe like the weird word.
yeah. So if your loss function is going down, and then up, you're probably overfitting. Yes, sir.
How do you use machine learning in script
So we just started doing that. I work in the security group, and there's stuff in security called anomaly detection, clustering, and a bunch of different things that we just started slowly implementing into. I can't speak in a lot of detail about that, but we're starting to look into those things. Anything else? First time, second time? Yes, sir.
Let's say you want to do feature engineering from, say, an audio file or an image on there.
Okay.
And you did something like, I don't know, you did like a SVD to find out anomalies in an image file
Sure.
on there, and then you relabeled it after clustering.
Sure.
Is there a way you can loop that into a neural network so that, let's say you have like a lambda layer that would
Yeah.
do the SVD function and then put out what the labels are and then continue on?
So I honestly didn't hear half of that. So let's take it offline. I'm happy to answer the question. I'm trying to answer simple questions just so I don't start going off. Yep, sir. Yeah, go on. Whoever the first person. Yeah.
Have you done any of the competitions on the data science site, Kaggle?
I started doing those. I haven't finished any of those. I usually start doing them and I don't finish them, mostly because a lot of time is of the essence. And if I do them, I'll try to do a team competition with a specific team of people. Yes, sir.
I was just gonna, have you come across the book Deep Learning with Python by the Keras author?
I did. I haven't read it. I heard good things.
I was gonna shout out for that because I've been reading that, and that is one of the, especially like you were talking about, how do you tell if you're overfitting? He
Yeah.
does a really good job explaining all that stuff.
Yeah. Honestly, I think that's a really good book. What I would recommend, if you're just starting out, is first do this part. It's boring at certain times, but it's needed. And then I would do all right. My internet is super fast. But there's a Stanford course from Andrew. That's a while ago. That I think it's this one. No, this is Duke. Oh, it's this one. It's an old one. It's a tad bit outdated, but it's pretty great. It does take a toll, and it does take a long time, but highly recommend it if you want to get into this. And then there's plenty of other ones after that.
They have a more up-to-date version that's 5-part, and it's in Python versus MATLAB.
Correct. They have one on I don't know if maybe I don't know about that one, but it calls deep learning specialization. Yeah, so that one doesn't cover all the things that this one does. I kind of like. I think that you should do that one after this one, even though this is MATLAB, and it's actually I like MATLAB because it does matrix multiplication really well. But you can go the other one too. It's just the first one I think covers a decent amount of what I talked about a little bit more in detail, because the second one is just deep learning. All right. Good, everyone. How do we? That's you can Twitter me. So I am on Twitter. I unfortunately don't have any other social media, but you can Twitter me on this handle right here. I'm gonna zoom in. So this one, and you can also email me, but I am really bad at answering emails. So just do Twitter. It's fine.
Can we use a Twitter bot to spam our question to you and answer it?
No. I am really bad at I usually answer, but it takes me a long time. So please ask all the questions, but it might take me a week to get to them. So you can catch me here if you want. I'll be around for a few hours. All right, cool. Thank you, everyone. Appreciate it.